So let's bring together all of this stuff we've been talking about for acidity so that we are able to look at two molecules and determine which of them is going to be the most acidic, or to look at a single molecule and say which of these hydrogens on this one molecule is going to be the most acidic, the first one taken off by a base. So, ranking acidity. The first thing you're going to look at is what atom is the hydrogen bound directly to. That is the usually determining factor, right? So here, if I'm looking at different elements in a row of the periodic table, so looking at fluorine versus oxygen versus carbon, now I'm thinking about electronegativity. So here, fluorine is fighting for electrons with this hydrogen and is doing a better job of holding those electrons than oxygen, which is way better than carbon. And so that ability to suck electrons into oneself can make it a better acid. So if you're comparing directly connected within a row, we're looking at electronegativity. If we're looking at down a column, so iodine versus bromine versus chlorine, all those halides, here we're looking at size. The bigger atom is going to give the stronger acids because that bond is weaker, because that big atom can stabilize that negative charge in the conjugate base. So here, HI is a stronger acid than HBr, a stronger acid than HCl and HF. Okay. So that's kind of, I think, the easier one, comparing atoms across a row or down a column. What about diagonal? Well, that's not really a good hard and fast rule. So I can't help you there. But we can use a periodic table for columns and rows pretty quickly. If we're trying to determine between atoms bound to, or hydrogens bound to the same atom, then we have to keep going. So the next most important factor is resonance. So for instance, here I am looking at OHs in both of these molecules. So the connected to the atom, that doesn't help me. But here I am able to have the lone pairs on oxygen in resonance with these pi bonds. What I mean by that is I can think about resonance between that negative charge in the conjugate base, or lone pair, however you want to think about it, as next to a pi bond. So I can spread that charge out into the ring in every other position. We saw this in class the other day. And so this is going to stabilize the anion. When orbitals overlap, they mix, and that mixing stabilizes the system, right? It lowers its potential energy. It is happier in a sense. So resonance is a really important thing. Here, for this molecule, this H right here prevents any conjugation or delocalization from these lone pairs in oxygen. So no resonance possible here. Pretty weak acid, unstable O-. So resonance is a pretty big factor, right? So here between these pretty similar molecules, five orders of magnitude difference in acidity. Even without resonance, we can have effects of electronegative atoms. So here, the inductive effect, there's no way for me to think about an O- or the lone pairs here drawing resonance structures and ending up with new electrons on fluorine. But while this oxygen can pull electrons through the pi system, these fluorines can kind of pull it through the sigma bonds, or really even just through space, not even through bonds. But having really electronegative elements anywhere near that minus sign in the conjugate base is going to stabilize the conjugate base and make it a better acid. Again, we went over this in some detail in the last video. So the inductive effect here, having 3 fluorines here compared to oxygens, it will lower the pKa rate by about 5. So that's a lot. Again, when you talk about an inductive effect, the strength of the electronegative atom makes a big difference. So fluorine makes a huge difference. Nothing on the periodic table is nearly as electronegative as fluorine. And so there's going to be weaker inductive effects beyond that. There's one more example of a trend in acidity that we should talk about that doesn't seem to fit in any of these three things, although I argue, yeah, it does. But let's take a look. Here I've got ethane, ethyne. The only difference is here I have a carbon-carbon single bond, here I have a carbon-carbon double bond, and here I have a triple bond. The first two are a little dissimilar, but they're both just really, really, really bad acids, right? So 40 and 48, those numbers are so big, it's kind of like 1,000,000 and then 1,000,005 or something. This one, though, is very different. In this, what we call an alkyne triple bond, this CH is way, way more acidic than any of these other CHs. So what's going on here? The difference is in the hybridization of the carbons. So here, when we talked about hybridization, we said this carbon is sp3. So you basically take 3 pi electrons, mix them with 1 s electron. That's the best way to describe this bonding. And so the consequence of that is that if I were to say, what's the character, how S-like, how P-like is this carbon, you'd say, first of all, that's a weird question. But to answer it, you'd say, well, it's about, if it's sp3, 1/4 of those orbitals was s and 3/4 were p. So I guess 25% s, 75 p. And then down here, the alkyne is just sp. We took 1 s orbital, 1 p orbital, mixed them up, and so it's 50-50. Think about the difference in nature, right? So the s orbital is just a sphere, and it is really tightly packed onto the nucleus itself. The p orbital is by necessity more spread out, more diffuse. So if you think about it, I really want to stabilize electrons by putting them pretty close to that carbon nucleus. This carbon, this sp carbon, is going to be able to hold electrons closer to its nucleus because it has more s character. It's more like this one. This one, it's much more likely to have those electrons kind of diffuse and spread out, and so it's going to do a really bad job at stabilizing some negative charge in a conjugate base if we take away the hydrogen. So in a way, and this is my argument for why it's already covered here, in a way, this carbon is kind of not the same atom as this carbon is, because this carbon has more s electrons. It's essentially more electronegative. Not all carbons are created equal. sp carbons are more electronegative. They hold electrons closer together. That's what it means. And so in a sense, that fits in with this very first row, right? Within a row, within a row is the kind of mnemonic that we use, but in reality, we're looking for electronegativity differences between atoms. So just like fluorine is better than oxygen is better than carbon, so also sp carbon is better than sp2 carbon is better than sp3 carbon. Your book makes this a 4th category and calls it orbital hybridization. So if all else fails, think about the hybridization on the atom. sp is more acidic than sp2, is more acidic than sp3. But here, I kind of think of it as just a difference in electronegativity, because this alkyne carbon is able to hold the electrons closer than these sp2 or sp3 here. So memorize like this if you like, but I really think that O belongs up there. This is how we're going to look at, again, 2 molecules and figure out which one is more acidic. We'll look at the 2 atoms and say, okay, are these hydrogens bound to the same atom or different atoms? If they're different atoms, or if they're even different hybridization of the same atoms, I start there. They're same atoms, then I say, okay, what about resonance? Is one of the conjugate bases stabilized by resonance? Can I push those arrows around? If there's no resonance difference, okay, let's go to the inductive effect. Is there some really electronegative atom, like especially like fluorine, being able to pull electrons away from where that negative charge would be? Okay. Again, if you strike out there, you can go, oh, and just double check that there's not some alkyne there waiting to fool you.